video. So each bit, like each character, is transferred into bits. Like each character has 8 bits in the ASCII form. So here as there are 20 characters, it's like 20 into 8. Total of 160 bits is transferred from to the target system through the network. As there are a lot of repetitions in the string, instead of you converting or sending each and every character through ASCII, we can make it in the recursive form and transfer one instead of all. Like if there are 10 particular ways, instead of transferring each A ASCII bits, we can transfer one ASCII bit of A, one ASCII bit of B, one ASCII bit of E, and one ASCII bit of W, which is in the recursive, so that we can save some bits uh, in the network to get transferred. To decrease, to follow, to implement it, we use Huffman encoding. In the Huffman encoding, what we do initially is calculate the frequency of characters. Here, the frequency of characters is like 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of frequency of A is 8 is 12. Coming from B, it was like 3. E, it was 3, and W, it was 2. The next step would be our target or our goal is to build a system in such a way that this number of bits getting transferred is to be decreased. So we have to build a tree or in structure in such a way the highest frequency. Here we have the highest frequencies for A. So number of highest frequency has the less number of bits. As it's getting invoked frequently, it should have less number of bits while drawing the tree. Uh, Let me make it more sensible. Yeah, if you see here the number of frequency of A is 12, W is 2, B is 3, E is 3. We can have it as 160 as each character is having which has to go 160. Now applying Huffman encoding, we have to sort this in an order, like descending to ascending, like A12, B3, E3, and W is 2. Now we have to construct the graph in such a way that this high frequency has the less number of bits when it's getting called. This is because the calls to this particular character is very frequent. As it is very frequent, if it has a less number of bits, the transfer would be an easy thing. So the highest number of frequency would have the less calls. This is the main goal which we have which the main theme of Huffman encoding which we have to follow while doing Huffman encoding. Here if you see A, B, I have written let's draw it. Let's clean it up. That's no problem. Let me try it here. Yeah, A is 12 and B is 3, E is 3 and W is 2. The highest frequency should come in the last step or the last level. We have to first build the graph for the lowest frequencies. Here the lowest frequencies are 2, 3 and 3. So you can build for this 3 and 2 or this 3 and 3. It's up to you. Let me start it from this end. It's up to you how you draw. but the main goal is to have the highest frequency would have the less number of characters, less number of bits, so that is the main theme of Huffman encoding. So this is 3 and 2. When I draw it here, it becomes 5. And the next thing would be 3 and 5. It would be 8. And when I add this up, like 8 and 12, it would be 20. The way we consider the bits, this is how the notation, it's up to you how you follow. Like we can take left is 0 and right as 1, or left as 1 and right as 0. It's up to you how you use it. I was using this notation here. So here I would get it as 1 and 0, left is 0 and right is 1, left is 0 and right is 1. So if you see, this is high frequency for us, and it just had one bit to get invoked. And if you see, the W is the lowest number of frequency, it's just 2 for us, and it had 3 bits to get called, like it has 3 bits. If you see A or B, E is also somewhat less when compared to 12. It also had 3 bits, like this is how it comes 1, 1, and 0. If you come to B, it is having 2 bits, 1 and 0. This is how it comes. Yeah, which is having frequency of 12 with 1 bit, 0, 1 bit, its bit is 0, it's 0. And with V, which is having frequency of 3, is having 2 bits, which is 1 and 0. And next is E, which is having frequency of 3, is having 3 bits, 1, 1 and 0. W, which is having frequency of 2, is having 3 bits, 1, 1 and 1. This is how it looks like the table. A 12 is 0, B 3 1 0, E is 3 1 0, and W is 2 1 1 1. Now, when we calculate the number of bits for the data, here it comes into play. As we have constructed this table, we might know it, but how could the end system or the target system should also know this table, right? So while transferring, you should transfer the data as well as the table here. So to transfer the data, what comes into data and what comes into table? Data, like we ASCII have its own 3 different characters for A, B, E, and D, W, but we have different bits here, like 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. So this, as the new bit for this, the end system should know this. This is what the data comes into play. Data part, and coming to the table part, as you know that each character is taking 8 bits, like 8, and there are 4 characters, right, like which are repeated. These characters are repeated. Previously we thought 20 characters into 8. As there are repetitions for these 4, we make it into each we are taking 1 1 1 1 and calculating it, right? So here comes like 1 to A, B, E, W, the number of characters of 4, and each character take 8 bits as ASCII code. And here if you see the number of zeros are 1, the number of bits in the table is for 12 it is 0, for 3 it is 1 0, 1 1 0 for E, for W it is 1 1 1. The number of bits are 1, 3, 6, 3, 9. The number of bits are 9, the total number of zeros and ones. This is the table part. The total number of bits getting transferred is the total of data plus table. So how we calculate this data? Now, let's see. Let's clean this up. Okay. Now data. We have this table right here with frequency and 0. Like initially, let's consider for A, it is having the frequency as 12 and the number of bits here is just the 1 bit is 0. It's for A. And for B, the frequency is 3 and the number of bits are 2. It's 1 and 0. So it will be 2 bits plus for E, the frequency is 3 and the bits here is 1, 1 and 0. It was 3. And for W, the frequency is 2 and the number of bits here is 111. Number of bits are 3. When you calculate 8, 12 it's into not 10, it's 1 bit, right? So 12 plus 6, 32, 6, and 3 is 9 plus, and it will be 6, which will be completely 33 bits. So I can do it apart. Coming to the table part, here it will be like, here it will be 2 parts. Let me take the cursor up. Yeah. A, P, E, W. There are how many characters? 4 characters. Correct? So 4 characters and each character is 8 bits. This will be one thing. And next, adding the total number of bits to get transferred. It is 1, 2, 3, 4, 5, 6, 7, 8, 9. It will be 9. Completely it will be 9 plus 32 is 41 bits. Now the total transfer bits will be plus table, which will be equals to 32 plus 41, which is 74 bits. Instead of transferring 160 bits, we have reduced it to 74 bits, which is the most efficient way to transfer the data from one system to another system in a network. You have seen 160, it is rather than more than half. Let me show you the full table. Advanced. This is the main point. Like this is frequency for data, the frequency into the number of bits. 12 into 1, 3 into 2, 3 into 3, 2 into 3. The total is 33. And the table, we are transferring the complete table. So how many characters do we have? The 4 characters. Each ASCII is 8. 8 into 4. And number of zeros and ones we are getting transferred here. 1, 2, 3, 4, 5, 6, 7, 8, 9. The total number of zeros and ones are 9. It will be 41 bits for table. Data will be 33. Total number of bits is 32 plus 41 is 74 bits. Thank you.